All right, time to get started. Welcome to the second week of lecturing, or the third week of the course. I hope you all enjoyed the workshop work. And let's just start the chat. And to give you some information, I extended the deadline with 24 hours. So the deadline is for today at 12 o'clock. So if you have not handed in yet, please do so. The reason was that there was some information missing, that you needed to log in to CoursePress to see the link. It seems that some people missed that. We had some late registrations that actually could not see the link even if they logged in. And we had some general confusion from some people, and I was not really available yesterday to answer that. So 24 hours extension of the deadline. So today at 12, we will be closing the form, and I will be informing you about the peer review process. And as a consequence, also the peer review deadline has been extended for 24 hours. I don't think you really need 24 more hours to fix your models, because I think they are, that's plenty of time really. So, but the deadline for the peer reviews are extended also with 24 hours. And as you can see, you should be able to see this link on the course homepage. And the 17th at 12 o'clock is the peer review deadline. And there will be another form for that submission. But I will be giving you some instructions on who you are to look at and how to proceed with the peer reviewing this afternoon. So keep a close look at the course homepage. As someone noticed also, we have the third lecture now. And this lecture is about software architecture. And actually all three lectures this week are probably going to be about software architecture. So we are leaving the domain model, we're leaving analysis, and talking more about how the software we are making actually is going to work. I hope that we will be able to do this in 3 lectures. I think we managed that last year. And this year we also managed to do the domain modeling in 2 lectures instead of 3 as we did last year. So we are 1 lecture ahead, which is good, because this gives us a little bit more time. That is also why we have 1, 2, 3, and 5, because I will probably change that when I know a little bit more if we manage to get all materials for lecture 3 done today or not. So there will be some coding today, I hope at least, but we will be starting by talking about software architecture. Any questions on the workshop or domain modeling or something like that? This is not it's not a new link. It's the same link as before. It was just that some people could not see it. So if you have already handed in your workshop for the first step here, you don't need to do anything. Any other questions? Was the modeling okay for the first workshop, or was it hard? Was it easy? So-so? Have some questions or comments on the chat here. I'll try to just a little bit. Is there any indication that the form has been correctly submitted? You should get some kind of okay, I think, from it's an ordinary Google form, so you should have some kind of this form has been posted at least. And I've not been in any situation where it has been a problem, but I can always take a look if you're really worried. So one group was confused about how detailed the domain model should be. And yes, that is, of course, a matter of debate. As you should think like a map maker, you cannot make it super duper detailed and have every little rock or tree on it. So you need to think about who is going to look at this model, who is the reader, who is the end user, so to speak, and adjust your level of detail for that purpose. For example, in this, the domain model probably does not become very, very large. And I also think that adding a lot of attributes, for example, is not that helpful. Attributes can be added in lots of different places, and you can probably find several tens of attributes that are quite meaningless. So try to stick to what is in the requirements and what is important in the requirements, and show the interesting parts and the hard parts and things that you have been confused about. I think that is one guideline, at least, you have in mind. Any other questions? Nothing on campus? No? All right, let's move on then. And feel free to ask questions anytime. Domain modeling is important. I think those few hours you spend on domain modeling to trying to understand the problem is a good investment. And always try to spend some time trying to actually understand what problems your customer have or your customer's customer have. This is time well spent. However, we are now going into software architecture and the model view separation principle. This is the agenda for the day. And now we are stepping into software again. So we're talking about how things are actually going to work. So the domain model, the analysis was about what is the problem, trying to understand the problem. Now we're talking about software again. Maybe a little bit more fun as we are software developers. So anyone heard about software architecture? What does this mean? Yes, no? Yes, no? Any idea? What could it be? Yeah? Yeah, the model view controller is considered to be one architecture or one way of dividing an application. Absolutely, absolutely. So what we're talking about here, and this is not an architecture course. You can go for full courses in software architecture. We're just going to have a quick look at it. Software architecture is about just like building architecture. It's not about exact blueprints on how the room layout is going to be or where to put the electrical wiring and that level of detail. Architecture is about the high level, the structure of the system, and we want to use this to discuss, for example, about system qualities. You always want qualities in your software. You want it to be fast, for example. You want it to be secure. You want it to not spend too many resources. You want it to be usable, and many, many, many things like that. And using software architecture, we can start discussing about these things and start modeling them, and also finding a balance between them, because some things are probably more important than others. And adding stuff towards the end of a project can be very, very hard. So we need to find the system qualities, and we need to find a balance between them, because they are sometimes contradictory. For example, we can make an early decision to make a web-based system because this is a familiar user paradigm. Users are familiar to web-based user interfaces, and we can make it usable and familiar to them. So we have a high usability requirement. At the same time, we might have very high security requirements. And this can be hard in a web-based system because we rely on many different servers sending messages over internet. It's an open network. We need to make sure servers are upgraded, database servers are maintained, and stuff like that. So by making the decision to do a web-based application, we can get usability, but we need to balance this probably with security. So finding a trade-off between those two is something that software architecture enables us to do. You have probably done a few projects on your own. I know at least the Kalmar students have done the individual project this spring. One common problem you have there is that at least towards the end of the project, you kind of like know, okay, this is the way I should have done things, not the way that I did them. Some of you maybe have not got that experience, but some of you have probably. And as you progress with your kind of like not optimal design of your system, you kind of like try to add stuff. But as you add stuff, things get more and more complicated. And at the turning point, maybe you even add stuff, but more stuff is broken. As you add more stuff gets broken. So you kind of like run into a dead end. So it is not enough to have a good low-level design or good implementation to have a good system. It is like having really, really good carpenters, really good electricians, really good plumbers, and trying to build a house. And they can make a really, really nice kitchen and a really, really nice bathroom and rooms and stuff like that. But they kind of like don't fit together in a good way. So the overall experience of the house is not that good, even though the rooms as individuals are good and nice. And this is the same thing about coding. You can have really good low-level implementation, really nice algorithms, really nice structure of your code at the low level, but it kind of like does not fit together in a good way. And this becomes more and more important as you add more and more developers to a project. If you are just on your own, well, then you maybe can manage. But if you're 2, 3, 5, 7, 10, 15, 20, 25, 30 programmers suddenly on a project, it is not that good that everyone is just hammering away at their little bit and later trying to get them to fit together. It's not that easy. So, and you often take a lot of early decisions in a project. For example, you decide on technical stuff. It should be a web-based system. It should be implemented in this language. We should have this database, this server. So you make a lot of decisions really, really early. And these decisions often have quite a large impact on the system you build. As I said, you have these qualities you want to balance, and making early decisions maybe too fast and just going along with them because they are familiar can put you in a situation where that is not that good. And so we want to use software architecture to find a good high-level structure of a software system that balances the qualities that we want, that enables us to have a good structure of our code, of the system, and to not make too early decisions without actually thinking about them, just not jumping onto familiar technology, for example, or new technology that is quite often that happens, that, oh, this is the new technology, we need to use this, without thinking about it, really. So we want to facilitate communication. We want our systems to be able to evolve. This is very, very important in agile processes. You need to have a system that you can expand, change, evolve. And this is something that you can focus your software architecture on. We want to have reuse, of course, and this can also be facilitated by having a architecture that enables reuse in different levels, so that we can have already tested, designed, coded components that can be reused in other projects. So we can deliver software a little bit faster and a little bit more secure and better. And also, this is the goal of the elaboration phase in the unified process. And this enables risk management. So the software architecture should focus on the riskiest parts first. So, for example, if you have requirements that, well, this system should work with 5 users and 5 million users, we don't really know. Well, then you probably need to select a architecture that is very scalable, because, well, chances are that you will only have 5 users, and you don't really want to pay for a lot of servers and bandwidth that is required for 5 million users to start with. So then you need to select an architecture that can scale much. And this is something that you should focus your architecture on, and find this early in your projects, not towards the end. So focus on hard parts in your systems. The software architecture should focus on the hard parts. These are often these qualities that we talk about. It is very hard to make a really usable system. We probably require a lot of deployment to end users, testing, changing, evolving. So then you need an architecture that supports these notions. So, and one way of structuring your software architecture, you probably have seen some kind of architectural diagrams, and they are often at a very high level. You often have a little cloud that says internet, and then you have a little cylinder that is a database, and you have a little computer that says server, and you have our arrows between these. And that is not really a very good way at structuring your architecture, because you're mixing different points of view. You're mixing, okay, how is the communication going to be? What kind of server software are we going to have? What kind of hardware are we going to have? And things like that. So the recommendation is to try to think about different points of view of your system. And the 4+1 view is a classical example of this. I think he mentions in the book the 4+n view, because you can add multiple views to this also. But typically you have the logical view, and this is what we are going to talk mostly about. This is how to structure your implementation or your classes to fulfill the requirements of the system. So high-level structure of classes, how are we going to organize our projects, our high-level structure of in our development environment, and how are things going to be connected to each other. How can we connect these things? How are they going to talk to each other? You have the development view, which is also quite important for programmers, for example. This is how to structure your source code. Where are we going to put files on the disk? How is this going to be organized? What kind of APIs are we going to use? Frameworks, versions of these frameworks, how are we going to build the software, so to speak? We are not going to talk much about the development view in this course, but as we are programming, you are going to see some things about it. And sometimes also the logical view and the development view are codependent. So when you do things, decide things in the logical view, it also affects things in the development view, depending on, for example, what kind of language you have implemented things in. So we have the process view. Here we decide on what kind of processes we are going to use. We are going to use a server process, and we are going to use a database process, and these are going to communicate with each other in this way, and we are going to have these kinds of help systems and things like that. We are not going to talk a lot about the process view in this course. And we also have the physical view. That is, how are we going to map these processes onto hardware? So what kind of machinery are we actually going to run this on? Specifications on these machines, and that can be more or less important in different projects. If you're shipping, for example, your application to a web hotel, well, then you probably have a lot of these things already decided for you. And to tie things together, you have the scenario view. And do you remember what the scenario is? To be more exact, it's like one path through a use case. You often have the main success scenario, for example, so it is one path through a use case. And you try to find the most important, the most risky scenarios in your system. And you start with these, and you show the software architecture by looking at these requirements. So, for example, if you have very high demands on security, maybe you should take a look at the login scenario in your software architecture. And you show how are we going to structure the classes for this scenario, how are we going to structure the code for this scenario, what processes are involved, are the communication protocols between these processes secure, what kind of a hardware are we going to have for this scenario. So you build your architecture based on the actual requirements from your application. And you show how are we going to meet the security requirements with our architecture. Questions? So let's see if I've forgotten to say something. Yeah, we could talk a little bit about what's in these. I hope this will work. Yay. So in the logical view, we talk about classes and objects mainly, possibly packages. So we make diagrams that contain packages, classes, and objects. You have already seen, actually, class diagrams and objects in the form of sequence diagrams from the first lecture where we did the dice game. And basically, this is what we are going to do throughout the rest of the course. We're going to draw class diagrams, organize classes into packages, look at how objects interact. In this view, we often talk about components, and components in the form of the things that we develop and package, that is some kind of a compilation or collection of classes. Also components in the form of reusable components, for example, APIs, libraries, components that we can buy or reuse from other projects. And here we have execution. So we take the components that we have, that we get from the logical view and the development view, and we map these onto processes and tell, okay, this component is going to run on this process. So the database component is going to run on the database server. in the database processor. And here we have computers, network, and hardware. So we get a question here. Packages equals namespaces in C#. Pretty much yes. I think in Java they are even named package. So often a namespace in your implementation language can be considered a package in the logical view. As you see, being a software architect is not that easy. It requires knowledge about all aspects of software development. You need to know about computers and hardware and network. You need to know about processes and process intercommunication protocols and stuff like that. And you need to know about how our programmers actually want to organize their work for their convenience. And you need to know how to structure your system also. So you don't really become an architect by taking these lectures, but we at least can start talking a little bit about it. And we also kind of like need a way to manage our software that we're going to create. We need some kind of way of dividing them so that they don't become too complex. And basically we're going to focus on this part, the logical view. So if you are interested in software architecture, the other parts, well, I recommend courses in software architecture and expanding your knowledge as best as you can. All right, how to... So, the logical architecture then. So we want a large-scale organization of classes into packages. And we do this by finding the logical groupings of classes that collaborate closely. We try to encapsulate these further and then define valid dependencies. So, go gadget coupler. So we find that we have, well, up in this corner we have these classes here, and they're kind of like interconnected. And we have these classes over here that are really connected to each other. And why not add this one also? And between them we have some connections, but maybe not that much. And we could add in a third corner also some classes. So the idea is that, well, when we have the design of our system, we can see that, oh, this bunch of classes, they collaborate closely. They kind of like do the same thing or help each other do the same thing. And then we have another cluster of classes that do something else, have other responsibilities. And they collaborate closely to fulfill these responsibilities. And we have a third kind of like a cluster. So we have these clusters of classes that do the same thing, and they collaborate more closely, but they also do collaborate between them. So what we would like to do is take a look at these collaborations. And these two. and try to formalize them. So instead of them being directly into classes maybe here, we try to find some kind of interface or something like this here. And this is the only thing that we would like to show to the outside world. So they connect to this interface instead. And we make up rules and regulations on how this is going to happen. So for example, we could say, oh, if you put something in the green cluster, you can only call certain functions using this interface into this blue cluster. You cannot call things from the blue cluster into the green cluster. That is not allowed, because we want to keep this structure, this integrity of stuff. And this is something you need to tell to the developers, so that, okay, I'm making this green, this new green class, and I need to know where to put it. So I don't put it in the black cluster or in the blue cluster, but actually in the green cluster. So dependencies are not violated. I wonder how many will understand this picture later on. But that is another question. Why did this happen? So the problem is then, how are we going to do this? Because this kind of like requires us to have at least a fair amount of the classes present. Since we need to have a lot of the classes present to make this division, to find the clusters, to find the dependencies between them, and to organize them better. So we have kind of like a chicken and egg problem. So we can't do the detailed design, find all the classes before we have the structure that we're going to put them in, and we can't find the structure before we have all the detailed classes. So how are we going to do this? And also making a fully detailed design really early on is, well, that's maybe not that advisable in all projects. Any ideas? Well, we could have experience. Maybe we have done similar systems before. So we can take a look at those classes and the structure in those systems and think about them and think that, okay, this is quite similar to what we're doing now. This was not that good, so maybe we should change that and try some other approach. These parts were actually good, so we are trying to mimic that design in our architecture. So we can use experience, of course. So how many of you have experience of maybe you need like 5, 10 quite large projects under your belt, so to speak, to be able to make some kind of experienced decision? Not that common. Hopefully you will get some experience. But I don't know if it's kind of like this lower down. But we can find experience from others. And that is a very, very good thing. So you can use the experience of other developers, because we have been building quite big systems for at least 50 years or so. So by looking at how others have done things and described things, you can mimic their approaches. And this is exactly what we have in different design principles, design guidelines, and in software patterns. I think the book is all even named Applying UML and Patterns. And patterns is something that we are going to use a lot in this course, and most of the the remainder of the course will be about patterns. That is, giving you some kind of design experience by standing on the shoulders of others, so to speak, and learning from others and applying these patterns in your own projects and systems. So, software patterns, you can find them anywhere. It's very popular. You can find patterns for usability, for testing, for designing, for architecture, for programming. You can find anti-patterns, that is stuff that did not really work out that well, that you also can learn from. Anyone heard about patterns? Used some patterns before, maybe? No one? You probably have, because patterns have also moved into languages and APIs, so you probably have used some patterns without even realizing it. Sometimes they are really obvious if you know the pattern, otherwise they are not. So by learning about patterns, you also become better at understanding how other people have solved certain problems. And that is a good thing. And we can start reasoning about things, about choices we make when we design software at a higher level, because we can talk about these patterns instead of drawing diagrams that are really sometimes confusing to understand. Loose coupling is one of these principles that we will take a look at. So, a software pattern. Basically, it's a named abstract problem and a solution to that problem. So, we have a name for it. This is very important that you have a name. This enables communication so that we can talk about the same thing and know that when I say an abstract factory, well, then you know what that is. When I say observer pattern, you know what that is. So a name is very important. The other part is a pattern is something that is abstract. It is not a specific problem. It is not a specific problem in a specific project. Rather, patterns are experiences from several different problems, and they have taken this problem and made it at the highest possible level so that it applies to many different situations. And also the solution is not a specific solution, it's a solution to this abstract problem. In a pattern, you often find the motivation for the pattern. That is, when is it going to be used? When is it useful to use it? You have the structure, of course, and this is the solution. You have consequences, what happens when we use it. And importantly, these can be both good and bad. So things will happen when you use a pattern. The consequences are there to describe what will happen and what are the possible pitfalls and what is the good stuff. So it is not often the case that we can kind of like eat the cake and have it. And by checking the consequences, you can see that, okay, this will be the flip side of the coin, so to speak. And we need to watch out for these problems when we use this pattern. And you often have examples. So then, learning a lot of patterns is of course something good, but it is actually not that hard or what the work is. Oops. Why did not that work? Is it because I have this one open? Nope, that did not work. Anyway, I will go draw it on the on this slide then. So actually the work is to know the abstract problem, these you can find in books. probably can have them in your head also. And let's do this in green. So, but you don't find abstract problems in your systems. You find specific problems. You find a situation, okay, how are we going to solve this problem in our application? You don't find abstract problems. So your work is actually to take your specific problem what you find in your application. We don't really know how these objects are going to be created. How are we going to create this collection of objects? It's quite complicated. How is that going to happen? Well then, you can think about your specific problem and you can find abstract problems that match. You can read about the consequences. You can read about their solution. And this is hard work. Knowing a lot of patterns is, well, that's a good start. Being able to code is also a good start. But the actual creative work is this, how to come from a specific problem to an abstract problem. How to find the patterns that actually match your problem, that solves your problem. And let's do it in green. This is also often pretty straightforward because you find the abstract solution in the book. So when you have decided, okay, we are going to use this pattern, this should look like this. And the final part of your work is, of course, to make a specific solution that solves your problem. Maybe we should even say creative work. So this is what we're going to focus on this course. Looking at specific problems, knowing some patterns, applying patterns to these problems, and implementing specific solutions. And basically, this is the designing software with the help of patterns and principles and guidelines. I think it is probably a good idea to take a break, and we will start with the first principle, the model view separation principle, after this break. So, questions? No? All right, 15 minutes then.